I am back. So, hello there. Last time we finished up section 2. We did 42 and 43 last time. We're moving on to 3, differentiation of power series. He says, let y be differentiable, I suppose, as many times as you like, function of z. And then define this operation. It looks like take a derivative and then multiply by z. So for instance, on your function, you're just going to take the derivative and then after that multiply by z. You could do this repeated multiple times. So for instance, on z to the k, if you do it n times, you'll just get the power k to the n, z to the k. And then he's got a few questions here, basically just show that if you had a polynomial, you could treat that as an operator for this guy, and it would give you just the polynomial evaluated at the power if you do it once. So yeah, the polynomial is what's giving us multiple powers of this operator. But in that case, you would just get the function at the power times z to the k. So that's interesting. And then the follow-up after that is this is a multiple of e. If f is a polynomial of integral coefficients, then the sum of this series is a multiple of e. I guess that doesn't really have to do with this differentiation operator, but yeah, it's kind of a short section, chapter 3, or section 3, I should say. So then he applies this operator to 1 over 1 minus z, which is, yeah, this is going to say, it just expands like this, so that should be pretty nice. Yeah, if you do it n times, that makes sense. You would get these powers in front. Define fn as this. It's polynomial, degree n. With positive coefficients. And its evaluation at 1 is n factorial. Yeah, I don't quite see that I don't quite see that part. The polynomial bit makes some sense. I'm okay with the first part. getting here must be something obvious. Wonder if I try like I guess I'm going out of order. Maybe we could just go in order. So 44 was, you have this operator, if you put it into a polynomial and apply that polynomial to z to the k, you'll just get f of k times z to the k. So maybe we'll try to go in order. 44. So f is defined as this guy, right? It's a finite polynomial. Oops, z to the n. And then we also have our z ddz operator, which does this. And so we know that if you apply it n times to something like this, you're just going to get k a bunch of times. And each time it sort of corrects, like remultiplies by z. So you use the power rule, k comes down, and then it scales it back up. So what I would have done for 44, we're supposed to show that this applied to zk will give you just the polynomial at k times zk. Seems somewhat obvious. Like it's kind of clear that this is linear. So I would just, I would just say, yeah, here's f. Right, sorry. So the constant term, I guess you don't have this at all. But for z, I meant z ddz. And here I have like z ddz to the n. Anyway, that thing applied to z to the k. So you just do it linearly. You're going to get c0, z to the k, plus c1 times z dz, z to the k. But we know what each of these do in general. There's a rule for that. So of course here you're just getting k to the n z k. Like you already knew that in general from the rule. Here you're getting c0, zk. Here you're getting c1 with a single k, zk, etc. So if you factor the zk's out, you get, of course, f of k, z to the k. So that's kind of an easy one. He didn't prove it that way. He basically factors this and points out he says, suppose this guy had roots, or let's call him x, just so it's the same notation. Suppose this factor is like x1, x2 through xn for complex, possibly, roots. And then he did something like I want to say he probably applies this operator to one of these guys, or he makes the observation that like, I'll just see what he says. We're looking at 44, I believe. So he factors it, and then he points out right, this is our polynomial. So this is one factor of our polynomial. You know, when you plug in our operator instead of a variable. Oops. I don't know why I did that, but yeah, suppose you had a root like xv. This factor applied to z to the k is of course just, you know, k z to the k minus the root times z to the k. So you get this. And that's basically all he said. You know? So if you had a product of these, you know, applying one of the factors gives you this, and then as you keep going, I mean, this is now a constant. But as you keep going, you're just going to get a bunch of factors with a k in place of the variable, so you're just getting f of k. So just take the product now, and you'll get f back. Yeah, not too much to say for that one. 45. Take a polynomial with integral coefficients. The sum of the following series is a multiple of, you know, I'm pretty sure I proved this a long time ago in like a Lie groups class. This feels very familiar. But yeah, if, you know, it's some multiple of E as long as f has integral coefficients. Certainly feels true. I mean, I guess you could so these numbers are changing, right, on the top. If it had been just a constant, I wonder how I did this before. If, I mean, for one thing, the constant case is, that's not actually a multiple of E. Yeah, it is. Yeah, it is. So, I don't know, I'm just thinking, like, if you had this, right? I was like, oh, that's not a multiple of E, but it is. I'm sorry. I was just confused for a second. It's not C to the K. If it was like C to the K, then you get E to the C, right? But in this case, you just get C times E. So obviously true for constants. But we don't have a constant exactly. Huh. Yeah, we don't have a constant, but we will have multiples. Yeah, there's something obvious that must happen. I was gonna say, I wonder if we can do it by induction, but let's first just look at what happens with a line, I guess. If I had like mx plus b here, right? So we have mk plus b over k factorial. Oh, of course, it cancels. You see that? So you're getting you're getting just a sort of shifted version. So the first term is missing, but whatever, you can re-index. You're still going to get, I guess you'll get, what are you getting? K times, well, K starts at 0, so maybe don't do that, but it cancels, you see what I'm saying? And any higher order, when you split it up linear like this, well, that's not true, is it? What if I have K squared? Then you just get K times, and then this shifted thing. I was all happy for a moment because I noticed that, of course, this is a multiple, but this should be 2, right? It's just going to be like re-indexed. So instead of starting at 0, we start at, like this is obviously still E, right? The first term doesn't make any sense. It's like not there. I mean, we could write them out and see, but it's still E. So I feel like we're just getting M plus BE. That doesn't quite make sense to me. Something fishy happens here, but anyway. Yeah, I would expect this to be 0. Huh. Well, all right, we could write it out. You get 1, actually you get 0. You get 0 plus, then you do get 1. And then instead of like 1 over 2 factorial, we're getting another 1. Right? But anyway, these do cancel and give you the same series. Like, it gives you 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus da 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 da, which is the usual. It's the usual series for E. So I do get M plus BE. So the interesting bit is coming up next, right? We're going to go ahead and say that, yeah, that worked. Although, I'm a little irritated that it gave me the same answer. It doesn't feel quite true, right? Why would these be the same? I clearly made a mistake. But, I mean, the first term, you're just getting something that re-indexes, right? The first term is clearly 0, so we may as well have started at 1. And then if you do re-index, you just get the same thing. So that's okay. That's okay. Right? This is 1 to infinity, which is obviously the same as this series right here. So they both equal e. Yep. So yeah, that was the one thing you can do, I guess, to not change the number. So the interesting bit is going to happen right now if I had k squared over k factorial. Right? So the first term is gone, of course. Otherwise, though, you're getting like 1 plus 4 over 2 factorial plus 9 over 3 factorial. So now something interesting is actually happening. And I can't just cancel it, but I get, well, yeah, I get k over k minus 1. Like the first term went away. If you wanted to reindex this, that's fine. But you're still going to get, what is it, k minus 1 over k factorial? Something like that. If you just want to get rid of one of the, you get rid of the top factor. Then fine. You get k over k minus 1. Oh, did I somehow botch that? Yeah, I must have. Yeah, I guess I did. Yeah, you got to add 1 to k, not subtract 1. Sorry. Anyway. I suppose this factors though, right? This is kind of a kludgy way to do it, but you can see that this still works. So I'm getting e again plus e. So this time with k squared, we're getting 2e. I wouldn't have seen it from this, right? This is kind of actually confusing. This is 1 plus 1. Wait, no, it's not. It's 1 plus 2. So is it e plus itself? I don't think I would have recognized that though. So one of these cancels, you get 3 over ish. Yeah, this is not clear to me what's going on when I write it this way. But it is this formula that we can see either way, either like by inspection or just by, cancel that factor and reindex, you'll get this. And then it is linear. This is a very convergent thing. Plus they're all positive terms anyway. So yeah, and we're getting e as we just saw a moment ago. And here we're getting e just straight. So for k squared, you get 2e. So it's clearly going to keep happening, right? If we do it, I mean, should we do an inductive type proof, or we could just do it directly, actually, I think. What happens if I just take a power? One of them cancels. The first term is 0. I guess then what I had done was to reindex right away, right? So same thing. And are we getting like lucky with this? Because I can just use the binomial theorem. We're going to get a bunch of integers and a power of k, which if we reapply this n times. So this would be certainly smoother if I just use induction rather than what I'm about to say, but upstairs we get, a sum powers of k, you know, and we can see that since we saw that in a smaller case, this type of situation gave us, well, I don't know that it always gives us 2, you know. I don't know that it always gives us n minus 1, but for 2 it did. For this case, yeah, we could perhaps do something with induction. But in any case, you can see that these are integers. Those are going to become factors in front of a thing that clearly goes to e, or some multiple of e. So you are indeed getting some multiple of e. Even without proving it by induction, you can see that you get something that's an integer multiple of e. We could probably make that a little bit more rigorous, but I wonder what he had to say. I'm sure it was a lot smoother than what I just did. Oh, he just deduces from this previous line, of course. What are you talking about? He treats that as a, like, yeah, fk, zk, naturally, is the result of the previous line. We just proved that result, that you could apply f to this operator. And yeah, that's just a bunch of powers of z. Huh. Alright, that proof was a lot kludgier and didn't involve the previous result that we were just thinking about. But his previous result, if you missed it, was this guy. He's talking about the operator, like differentiate and then multiply by z. Differentiate and then multiply by x. If you do that n times against, say, a power, you use the power rule, the k comes down, and then you multiply by x, and it increases the power back to the original. So these functions, like power functions, are eigenvectors for this operator. So yeah, I was supposed to sort of recognize that this is the numerator in an expansion of E. That's a pretty slick way to do it. So yeah, we were looking at this, and we're observing that this part is, well, I don't want to say d dz. Yeah, it's like f of, it's f of this operator z d dz applied to z to the k, like that. Yeah, so we basically just went backwards with that result. This no longer depends on k, of course, so you're just getting this. if you do that, well, it's really just kind of a more succinct way of writing what we observed here. Because when you do apply this operator to e to the z, it's like applying it to, 1 plus z squared over 2 factorial plus z cubed over 3 factorial. So what's the point? Because I don't actually get integers here, but yeah, I'm not actually just differentiating. I'm differentiating and then scaling it back again by z. So when we do that to e to the z, yeah, it somehow doesn't mess it up, right? It gives you 1. Yeah, I'm still not quite seeing it. But his last comment was just that it gives you an integral multiple. Yeah, it's this. And he doesn't do the details out. He just kind of observes that it would be some, you're multiplying by some polynomial with integral coefficients. So it's not a multiple of e to the z, it's of course if we evaluate at 1, you do get a multiple of e. That's all we wanted to show, was that this series, if you plug 1 in for z, you'll get a multiple of e, which is true. Okay. I'm mostly okay with that. I guess my issue is we're differentiating, like we're doing this. We're taking some polynomial differential operator. But that's fine. Each time you, like we just saw that when you apply this, well, it just gives you this. We just saw this result. So you're going to get, I guess that's why I'm pausing, is because you're going to get like integer multiple in front of the original thing. It's not clear to me that you still get e. So here's my question mark, is like, why? How do you know that the e is still contained there? Probably a stupid question, but so if this was like just z ddz, weirdly you get 0, so that's gone. This becomes a z again. This becomes 2z squared. So it cancels. So are we? Oh, we're getting z times e to the z is what I'm saying. I see. I see. Hmm. Yeah. So why is this obvious? Um, I follow you up to here, no problem. I'm staring at this thing, and it's clear. Um, hmm. I mean, I guess it's somewhat clear because of what I just said. Like, so let's just do it in general. I did it with one power, but for example, if you did like z d d z k applied to this series, you take k derivatives. Well, not really. We can just apply it immediately. You're just gonna get, yeah, why are you thinking about this at all? Like if you apply this whole, if you apply this to z squared, you just get f of 2 times z squared. So actually, I don't need an example. I could just say this equals, for sure, well, it equals this. Yeah, it equals this. Yeah, I don't think he cites, he doesn't really say anything more about it. I don't think he has to. Like I was thinking maybe he used this trick again, but he doesn't really. He's just using the result of 44 to say this equals that. Um, hmm. Oh, I see. I didn't actually think about what this is if you apply it to e to the z, right? Because that's its own derivative, and then you're just scaling by some polynomial like z, right? So even if this was like you do it twice, um, yeah. That's what it is. It's basically the product, like a generalized product rule thing going on. This is not that hard. I don't know what I was thinking. But yeah, I guess it does require some thought, right? So like we're actually applying this. Like if you had z dz against e to the z, you get z times just e to the z, right? That's the easy case. If you do it again, like you can do this k times if you want. You'll just have not k terms, but like, so do it twice, say, right? You get this back, and you're doing it again to that. C e to the z, right? So now we've got a product rule, is what I'm saying. So that's why he's saying it's some integral coefficient polynomial times e to the z. Your product rule, on this case, your g to the z would be like z plus 1, right? Actually, I think it's z squared because we're multiplying by z after we do the product rule. So it's something like this times e to the z. So if you do it twice, you'll get 2e to the, well, 2e, which is actually what we saw when we did it explicitly out right here. Yeah. So there is something to say there. It's not completely obvious. From here to there, it's happening because of the product rule. If you differentiate e to the z, it'll just stay the same, but then you scale it by z, and you're potentially differentiating that a handful of times. But so what? You're just going to get a bunch of product rules. And notably, the coefficient would be an integer. Yeah, that wasn't as bad as I thought. But it did require a little bit of thought there. So like, if you did this, you don't want to do it k times, but eesh. I can see it's that. And then if you do it twice, this is obviously not the way to do it, but if we do it twice, we're getting, you know, a product rule on these puppies. So you're getting this. We do it again, you're going to get So on its own, this one term gives you z e to the z as a result. This one, you sort of need to use the product rule, and it gives you this whole thing back. So we're getting 2z e to the z plus e to the z, you know. And then again, this guy alone just gives you itself times z. That's what we did there, right? Unfortunately, this guy sort of expands and gives you e to the z plus itself. So like this part gives you e to the z plus itself. This guy in the middle gives you a z, e to the z. And this guy does the same thing. It expands again, gives you itself plus e to the z. I was hoping for a nicer pattern here, but no go. So this one was like, this is like 3 plus 2 of them. Yeesh. So 2z e to the z plus e to the z, right? This one's 3z e to the z plus 2 e to the z. And when you do it again, you're going to get, well, anyway, this is a stupid way to do it. These are all just equal to this original guy, depending on how large your k is, you know? But anyway, you can see here you're getting 2z e to the z, and then from this guy you get 3 of the dual terms, e to the z plus z e to the z, like that. So you end up with, what is that, 5z e to the z plus 3 e to the z. This is after 5 applications. So we get 1, then we get 1, 1, then we get 2, 1, 3, 2, eesh, 5, 3, etc. But you do still get multiples of e when you plug in 1. Not too much more to say about this. I'm just still kind of staring at it. Of course, we didn't have just this one term, so maybe this is a bit of a waste of time, what I'm thinking. We had a function, like we had a polynomial of these, but that doesn't matter, you know, it'll just be an integer multiple of this, or, you know, one of these lesser cases, you know. Take one of these and multiply by a constant, an integer constant. You're still going to get an integer multiple of e when you plug in 1. So yeah, there was something to sort of observe there. He didn't say it, but like obviously he's actually doing that differentiation out. He's at least thinking about it, you know. Luckily, e to the z is pretty easy to differentiate. I don't think I'm going to have luck with this 47 one. Or wait, 46? 46. So we'll take a look at it real quick. I have not seen these before. I don't think I've done this one ever before. Some of these I had done like a couple years ago, but this I would not be surprised if I've never done it ever. So, oh, sorry, here's the question. 46 is what I'm looking at. So anyway, define it like this. I mean, define fn as, excuse me. Define fn z by the previous, you know, so when you write this out, leave some space for this mess in the middle, but he's defining it as a polynomial of degree n with positive coefficients. Well, that I don't see. I understand that part. It's definitely a polynomial of degree n. But after that, you're going to lose me. So yeah, this is fn. Show that it's a polynomial, obviously of degree n. That part is easy. But it has positive coefficients. Except it's 0. And also, its evaluation at 1 is n factorial. So that's all I'm trying to show. That's number 46. Huh. So of course this is a geometric series, 1, z, z squared, etc. But then we're applying this operator to it n times. So you're getting 0 plus, so then the first time you get a z, you're going to get just 1 to the n z. Does that make sense? It's probably what's written right there in the corner, but that's coming from if you took this geometric series and then you differentiate, well, you're doing this operation n times, but what you're doing is use the power rule and then multiply by z. And you do that n times. The power will never change, but you will have n factors out front. So we're using, it's basically part of the definition that if you apply this to z to the k, you'll just get k n times. All right, so that's kind of obvious at this point for this differential operator. But yeah, what we get for a series is, shouldn't really write a, well, we get a 1. We get 1 to the n z to the, that's it, z. Then we get 2 to the n z squared, 3 to the n z cubed, etc. All right. But now he's saying, express that like this and use that to define fn. Fn is the numerator of this. All right. I mean, shouldn't I don't know. I was gonna say, shouldn't I be able to like express this using Taylor's series somehow and get this as a, it's not exactly what he's doing though. it kind of makes sense, right? If you were to normally differentiate without the z there, you would absolutely get this. With the z there, I'm a little confused, but he's claiming it still works. You just get a polynomial with actually positive coefficients. Huh. Did not see that coming. Well, what if I did this to our little series here? So I know it's this. I'm not going to undo that. But what if I try to get clever, right? And just multiply by 1 by our little series here. And in general, it's like v to the n, z to the v, right? Because that's just a binomial. I could expand that. So we get two series. We get binomial business here, -1 to the j, z to the j, right? That's 1. And then we get the series that I just jotted down, which I guess I'll rewrite. Like k to the n, z to the k. K goes from 1 to infinity. And over here, our j's actually begin at 0. So I noticed that right away. The other thing is just a reminder, these guys don't have factorials in the bottom. So from a couple days ago, if you have a product of two series, you know, two, I should say, power series, their product is a power series. The coefficients are given by this sort of cascading, intermingling thing. Sort of similar to the terms you see in a binomial theorem, right? It's pretty straightforward to show it. But those usually start, I mean, I guess we can start this at 0 as well, right? There'll just be a 0 there. So we can start at 0 if you like. So yeah, this will equal a new sum. But you said it's a polynomial of degree n. All right, we'll see. Oh, maybe this is going to cause it to be 0, though? Yeah, this is not infinity. This stops at n plus 1. Excuse me. Which means what? Well, it means for the rest of the terms, the coefficients are 0, right? So for anything above n plus 1, you're getting a product where one of the coefficients is 0. Anyway, over here we can write this, if you like, as ck z to the k. All right? And actually, it does, I mean, I would think it stops at n plus 1, but we'll see what happens, what goes on over there. I mean, we can write infinity if you like. That's clearly okay. But it is finite because at some point, in fact, it is going to be n plus 1, I think, which is wrong, right? We should get n. So I'll have to investigate what's going on there. Of course, at 0, this also cancels. Oh, it's going to cancel that n plus first term. Awesome. So no, we're okay. It's going to stop at n. That's my claim, right? Because when you do this cross term thing from the result I just showed you, this term is 0 when this term is n plus 1. well, here. So now you need a better explanation of what's going on with the CKs, right? CK would be, well, normally you would stop at K. So it would be something like A naught BK plus A1 BK minus 1, okay? Up to AK B0, like that. Okay, that's coming from, like, if you had, say, an infinite power series times another infinite power series. You get some new series that I'm calling C. Okay. When you multiply these, you basically just, like, to show this result, you would just be observing that these powers are coming from various pairings of ij, but only the ones where this occurs. So then you just go back and substitute, like that means the bi is k minus j, right? So the coefficients in front of, like the coefficients for z to the k, that is z to the I plus j, are coming from, of course, these numbers, but it's like this form, right? And then the last thing would be, you're just thinking about all the ways that could happen. So if, say, j was 0, I would have to be k, right? That's the smallest that you can get in this j direction. And then, of course, they go up in this cascading pattern. And finally, the lowest that you can get is if I was 0, right? If I was 0, then j is k. And that's all you get. So there are certainly more coefficients, a's and b's, but that's not relevant for this particular coefficient, right? So these coefficients follow this formula. That's about it. It's pretty straightforward. So so back to our question. These are my AJs, right? All these are AJ. In fact, at some point, the AJs become 0. Once j is larger than n plus 1, you don't even get anything. And over here, this kn is my bn. So our formula for our CKs for this particular question is something like, well, I don't want to write it as a sum. I'll just write out a few terms, okay? A0 would be like 1. It's actually 1. It's n plus 1, choose 0. Well, I read it a few terms, but you get 1. And then bk is k. Oh, sorry. I meant bk, not bn. Anyway, bk is k to the n, like that. And then the second term, a little more interesting. N plus 1, choose 2. Wait, what? I meant 1. Excuse me. Choose 1. There is a negative sign this time, so I probably should have just put it here, like it's a subtraction. Let's just try it again. K to the n minus n plus 1. And then over here, we went down a degree in the k, so it's going to be k minus 1, like that. Then you get a plus, n plus 1, choose 2. k minus 2. And this continues, well, sadly it depends on how big k is, right? If so at some point, the biggest this gets, let's stop a little early, n plus 1, say choose n. All right, so here we had j is 0, j is 1, j is 2. Sorry, up here, j is 2. Finally, we get to j is n. We're going to have this. We're going to have a negative 1 to the n. And then we get k minus, like k minus that j value. So here it's k minus n. And we would normally keep going up until k, like up to k minus k, basically. We would keep going until you get b0, right? Normally. But here we're being stopped either by b0 or by j. Like this is going to be the last term that you see is 1 times negative 1 to the n plus 1. And yeah, technically there's I don't have room to write it here, k minus n plus 1. That's the last term. Oops, this last factor. You don't have to go any further because these are 0 from then on. The AI's, like if you plug in a sub n plus 2, you're going to get 0. So this is finite. I mean, it was always going to be finite, but if k is less than n plus, if k is bigger than n plus 1, it kind of caps off at n plus 1. But yeah, here's a pretty general term. Is this really what you would always get? Well, no, for small k, probably confused us because I called this k a moment ago. But for small k, you could only get like a couple terms. You know, you don't have to use all of these a terms. So if k was less than n plus 1, if k is less than n, you know, then you don't use all of the AJs in this formula. You just stop at whatever k is. So what that means is the b's might be funny. Okay, like you could choose this value to be, that's weird. You could let ck be like, say, 100. You're going to get 1 times 100 to the n. And then as it goes down, you're not going to reach b0. You're actually going to stop at 100 minus n, basically, or 100 minus n plus 1, something like that. So you're going to stop at this term, is what I'm saying. Camera froze. Let's see if I can get my camera back. Nope. Let's try this again. Here we go. Are we live again? Yeah, we are. Okay. Sorry about that. So we made a couple observations that it's a degree n. I kind of believe that because I was muttering it before. If you're looking at b sub 0, namely the largest possible term that you get from the other coefficient, b sub 0 is 0. So you actually never see this last term. I wonder what that doesn't make, sometimes you do, right? What if k was really large? I was just saying that that's what stops it. So I think you do see this n+1 term, but you won't see it as a power of, I mean, all right, let's see what happens. What is c sub n+1? It would be, I mean, let's just go in the normal order. A0 would be 1, and then this you would get, yeah, it seems like I'm getting, I mean, that's just a number though. Yeah, I'm getting something. I'm getting something non-zero, right? BK. C n+1 would give you this evaluated at n+1. So I'm getting n+1 to the n. I'm pretty sure that's right. Plus a1, b, like what I'm saying is you get a0, bn plus 1, plus a1, bn, plus a2, bn minus 1, etc. And then you can actually stop at an plus 1. Well, we were going to do that anyway. But like that. That would be the formula. I'm just surprised that this term survived at all. I was hoping, what? I mean, I was hoping this would be 0 because that makes my life a little easier. So is this n+1 instead? I mean, I guess not, right? Because at n+2 you'll get a similar formula. Strange. I felt pretty good about this. Yeah, what happens is, yeah, it doesn't always match up, you know. Like when we get over here, this term will be 0, sure, but you still got all this other stuff. So there's also a minus sign here, but that's okay. We'll move on. n+1, 1, -1 times, and then this goes down 1. It's bn, which in our case is n to the n. Yep, it's to the n. It's because this was n+1. That's what we started with, was stuff to the n, because this is applied n times. So these are always powers of, these exponents are always n. So this is n to the n. And the next term is going to be n+1, choose 2. We can write it down, I guess. n minus 1 to the n, yada yada. And this last term is actually going to be a 0 because b0 is just 0 to the n. But the last term that you do see would be, looks like an, -1 to the n. And there's a 1 here. 1 to the n is what the b1 would be, right? b1 is 1 to the n. Man, keep writing stuff you can't see. So yeah, that's what you would get for the last term on this. Do these cancel somehow? That would be nice, but I don't think so. So that's one thing that's frustrating me, is that I get this mess for cn+1. I was hoping that they would all just be 0, because I'm trying to show that this thing is finite. I wrote an n here, but I mean, sure, technically it's infinity. But that's making me sad because I thought this would be a polynomial of degree n. And then the other things we want to do is like plug in 0, see what you get. Plug in 1, see what you get. If you plug in 0, why would you get 0? All right. I should take a look at his answer because it is getting late. Yeah, did he do something more clever than what I did? We're looking at 46. Functions are connected by this recursion formula, and therefore blah. And he did not do at all what I did. I noticed this recursion relation between n and n plus 1. And apparently the rest of it falls out from there. Really? Well, I'll double check that. But I wonder what's wrong with what I did. I don't think anything's really wrong with what I did. I must have just... I mean, what could be wrong is that it's just too hard to do it this way. But that's not really true. And this is a power series, so what do you want? What was wrong with what I did? Clearly, it's going to give me the same answer. It might not be as obvious though. Like I might not be able to do these parts, but I should definitely be able to tell you what the degree is. Maybe not. Maybe not. Maybe you just can't see it this way. Anyway, it's not... What's the thing is, like, it doesn't look that bad. And I had hoped that this would work out to be 0 somehow. It is symmetric, right? Well, not quite because of that 0 term. But regardless, there's a bunch of terms that repeat themselves, so like these are the same. But they're not, because it's stupid n to the n. So it's not like they're just going to cancel and give me 0. Well, wait a minute, do they give me maybe the negative of this? That would be cute. I wonder if they do. Because this is very similar, right? It's off by 1. What's that? what is it like? NR is the same as n minus 1, R and R minus 1. This is an identity. So I can replace these with this sum. That's pretty nasty. I'm just wondering now if I can expand this first term and it actually cancels and gives me 0. Because then I could at least like check this part off, you know? And then the other stuff is like, well, when you plug in 0, you get the sum of all the coefficients, which is going to be a bit of a bear. But I didn't write it down very well, you know? I didn't write it down very cleanly what it is. So actually, these two might still be doable. So we know it's this in general. Let's just try it again. I was looking at what is it? Z minus 1 minus z. Sorry. Whatever. 1 minus z to the n plus 1, right? Anyway, that's times. That's not the important bit. It's times. I did a binomial theorem on the first part. So we're getting n plus 1, choose j, and then this is negative z to the j. Okay? That was the first series. The second series is the infinite series coming from the question itself. This guy, but after this differential operator is applied to it. So you get a geometric series, and then each step of the way, this thing is applied to it. So it just kicks out that exponent however many times. In our case, n times. So you're getting like z plus 2 to the n, z squared, 3 to the n, z cubed, etc. You know, 4 to the n, z to the 4, etc. That's the series that's going here. So we wrote it as, in fact, let's make it a little clearer this time. It's I to the n, zi. You can start at 0 if you like, but this is an infinite series because it was coming from just a geometric series. It's 1 over 1 minus z, but with this differential operator applied to it, okay? And then we're trying to write this as a new series. I'm calling ck, z to the k. So this is the stuff that was there, and then I'm being clever trying to introduce this 1 minus z to the n plus 1 in this way. So this product is 1, of course, right there. So we're there, right? And then there's a formula for these CKs. Of course, it's just like A naught BK plus A1 BK minus 1, all the way up to AK B0. That's in general. I mean, that's what it is, but we're going to write that as a sum. Lord help us. So IJK, I'm running out of letters here. Let's do I from 0 to k of a sub I, b sub k minus I, right? That's all it is. But our, this is a sub j, and this is b sub I, right? So for us, this series is remember I'm also hoping to show that like for values of k larger than n, that this works out to be 0 somehow. This formula works out to be 0 for some reason. But the things we want to show are that like the sum of the CKs equals, was it 1? I think it's actually n factorial is the question. You can see it better than I can. It's up here somewhere. fn1 equals n factorial, I think. Yeah. So I want to be able to, if I plug in 1, I get n factorial. And I also want, if I plug in 0, I get 0. Well, of course I do. That part's not bad, huh? I should get C0. What is C0? 0. It's because of this term. Let's double check that. I mean, I know it's 0, but like, no, it's 0 because like there's a z here. There's no way to produce z to the 0 with this term there if we're multiplying by more, powers of z. So yeah, it is 0. So we get this one for free. This is easy. I didn't realize that. So of course f of 0 is 0. But we want to show this. And I also want to show that ck equals 0 when k is bigger than n. So I'm doing it my way instead of Cesaro's way. I shouldn't be. I need to go back and understand what he did. But this is what I did, and it really should work. I don't know why it won't. It doesn't look like it's not a tractable problem, right? So like AI is going to be n plus 1, I, alternating, I. That's the AI bit. And then bk minus I is just k minus I, like that, to the n. So that's our sum. Like you have to take the whole sum just to get the one coefficient, but big deal. And I'm trying to show these two things occur. If you were to take a double sum over all the k's, somehow you get n factorial. But I also want to maybe show that they vanish completely after n. Is that clear just from what I just wrote down? What if you're at n plus 2 or something for k? You get some stuff that doesn't make sense. I mean, you get some stuff that is effectively 0 here. But it's not all 0, right? Because I is changing from 0 to, say, n plus 2. The first n plus 1 terms make sense. They give you something. In fact, this gets bigger. This stays big the whole time. It stays n plus 2 minus I. Damn it. So I guess another thing that I didn't want to have to do is I could expand this with another binomial theorem, right? We might have to if I'm going to try to show that it equals 0. Because we just looked at it and it wasn't clear that this is 0. Damn it. Say, this is why you do things the smart way. This is why you listen to Cesaro and not just follow your instinct. Follow your instinct into the abyss. Anyway, I at least phrased it a little better this time. I guess it is true that once I becomes greater than n plus 1, you're going to get 0. And once, well, that only happens the once, though. When I equals k, you get 0. That's that last term we were talking about. Don't we stop at that point? Yeah, of course we do. So you could have like not a full representation of these binomial coefficients. if k was less than n, say, or n plus 1. And it never gets a chance to even hit them all, but that's fine. I don't care about that. Yeah, I wanted to hit this second thing first. This is alternating. We haven't seen this before, this power of n. We've done similar stuff. We've been doing a lot of that recently. This was squared, so that's not what we're looking for. I don't think he had one where it was stuffed to the n, you know? These were about as weird as they got, these identities. So here's like an alternating bit with a harmonic coefficients. Here's an alternating with growing integer coefficients. And that's about it. Then you got the more basic ones. And then, of course, this identity. And that's about it. So you could maybe use something like this if this stupid k to the n was not in the way. I suppose it kind of looks like if you took n derivatives, right? Well, no, because it's not factorial. It's coming from this operator that we used, right? The z d z thing. So I was thinking, oh, we could take like a geometric series and differentiate it, but we're not actually doing that. We're differentiating and then multiplying by z. So that's why this power is here. Like, you know what I mean? That's why it's a whole, it's the same number again and again and again. So I'm not going to be able to just differentiate. I could try to look at this operator, you know, the z ddz operator against, but that of course is what we're doing. Yeah, kind of circling around it. Man, I wonder why I can't just do it directly. Well, so his claim is, of course, this would be 0 anytime k is greater than, or even, no, it is degree n. So if it's greater than n, he's saying this should collapse somehow. So on the other side of the paper, I was looking at n plus 1. And, you know, here we'll get this sum up to n plus 1. This will be n plus 1 minus I. Let's see. The 0th term is there, but the n plus first term is not there, right? Because you get 0 over here. So if you want to just skip right to this case, we can do that. Because you'll never get k equals n plus 1. I'm sorry, I equals n plus 1. You'll never get that case because k is also n plus 1. So we're looking at this, and then you have this k minus I. Man, this sucks. I'm just going to have to use the binomial theorem on this mess and pray that something happens. I guess. Yeah, man. All right. So this alone would be, let's say j from 0 to n, and choose j ish. This is ridiculous. Negative I to the j, k to the n minus j. Yikes. Well, it is what it is. That's not really important. It's also an integer, so you know, this is not. Yeah, what was I thinking was, what was I hoping was going to happen? I guess I was hoping that this integer would somehow coincide with this binomial coefficient and cancel out part of the time. Which it could do, but like, Anyway, if you look back at this, you're getting 1, 1, and then this is 0, so you get n plus 1 to the n. Is that the same thing we started with in this? Yeah, it is. Plus, well, you could say minus if you want, minus n plus 1 times just n to the n, plus, finally we get something interesting, n plus 1 choose 2, times n minus 1 to the n, etc. And the last term that you actually see is negative 1 to the n plus 1 choose n, and this is a 1? Yeah, 1 to the n. Now these do match up, but there's an n to the n there. So actually, I don't even know that this is different, right? What if n was odd, for instance, and they're both negative? It's okay, there's more terms. Yeah, this is sucking. I don't have a clever way to look at this series anyway. Because like I was mumbling before, usually the clever way to look at it would be to like take derivatives of, you know, 1 over 1 minus z. And you can express it both as a binomial theorem, and you can look at the derivative and say, okay, these must be equal, and so now we have a formula for, and that's how we did like one of those questions with binomial coefficients with like integers in front of them. But ours is like to the n. Yeah. I mean, in any case, I sort of know that this has to be 0, right? Like this equals 0. I can't show it, but evidently this is true. Can I get the other one? Why would I be able to get the other one? Like if I sum this as k goes from 0 to n. Let's see. If this was 0 and this was k, I goes from 0 to k. So you're talking about this region. And then we're going to sum as k goes from 0 to n. So there's a cutoff somewhere, n. So yeah, I'm giving up. I was going to look at this one now. Let the k's go from 0 to n of our ck formula, you know? I don't see anything nice about it, as usual. I thought maybe we could exchange or interchange the order of this integration, and maybe we'd be off, but I guess not. Sad news all around. I is going from 0 to k is going from 0 to n. So if you want, you could change this to be like I goes from 0 to n, and k goes from I to, but I don't see that helping us. K goes from, I suppose, I up to n. Sure. So that's out. This is out. And now you're just summing this part. It looks like, yeah, it looks like 0, 1, 2, all the way up to n minus I. And then we're still changing over I. So I'm looking at a sum like it's sort of like 0 to n minus I of this. You know, it's 1 plus 2 to the n plus up to n minus I to the n is what this stuff is on the inside. But anyway, I still get this junk, which is intractable trash. And then we get this sum I was just talking about. And evidently, that's n factorial. Sure it is. Sure. Well, all right. This is the wrong way to do it. I give up. I'll read the damn book. Sometimes you have to admit defeat. So I'm going to spend this last 10 or 20 minutes trying to understand what he did. So from Cesaro, I'm confused. Is it a book by Tobner in 1904 contains this result? Functions are connected by this recursion formula. So you say, therefore, the coefficients are linked by these relations. And then in the first case of n equal 1, you apparently just get z. So this would be, that settles fn1, that last line takes care of the n factorial bit we were just looking at, sort of. But yeah, I would need to know why this is true. And so what are we doing again? We're looking at, we're trying to, well, sure. We're trying to express this as a function over 1 minus z to the n plus 1. Now in particular for n equal 1, you just get so that's what happens when you differentiate and then multiply by z, this function. So take your regular geometric series and multiply its derivative by z. So we would normally have 1 plus z plus da da da. If we differentiate, we get 0 plus 1z. Wait a minute. 0 plus 1 plus 2z plus 3z squared, right? So that's where that comes from. And then he's saying this is just z times the usual expression for 1 minus z squared, which makes sense, right? The expression for 1 minus z squared just comes from differentiating the power series. So you would also get, you know, this. I agree with him on this trivial point that this is the correct function for n equal 1. Because, you know, this squared, the formula for that is like this. So we're getting that. Or not this, but this. That's what I'm saying. So we take this and we multiply by z. Yeah. That's right. Take this series, multiply by z, you'll get that. So that explains that stupid part, the easy part. So yeah, he's saying if you go from n to n plus 1 in your formula, he's claiming, I'm not claiming, but Gisaro is claiming that you'll get this relation, derivative times 1 minus z plus n plus 1 times fn. Okay. What? Why would I have noticed that? I mean, what the heck? If I differentiate this, if we differentiate your relation, maybe I should multiply by z after I differentiate it. Is that where that's coming from? But yeah, if we differentiate this mess, we get right. It looks like it's a bit like k to the n plus 1, z to the k minus 1 from, I suppose, 1 onward, right? If you differentiate the right-hand side, you'll get fn prime. Huh, he didn't even factor. You think he divided? I'm confused. Maybe he multiplied by 1 minus z. Anyway, I would get top times bottom minus the top times the derivative of the bottom. The derivative of the bottom looks like n plus 1. Well, there's a negative sign there, isn't there? Yeah, it's not going away. This times 1 minus z to the n, right? So that's just a quotient rule on this right-hand side. You can... If we multiply this by z, okay. If we multiply both of them by z, both sides by z, you get you almost get your original series back, except the powers are increased. That's cute. Okay, so obviously, if you just do it again, you get the next iteration of our formula. Yeah, that's why he did it this way. Yeah, this makes a lot of sense now. But yeah, what are we doing? So if you multiply by z, you just get the n plus 1 version of the left-hand side. I'll just call it that. Same formula, but with n plus 1. Does that make sense? Yep, it does. So multiply by z, it'll correct this first term and put you back in n plus 1 land. But on the right-hand side, we'll get this stuff, actually almost what he wrote down. Let me do this. There we go. Right? We get that on the right-hand side, but we also know that we're supposed to get fn plus 1 over, I guess, 1 minus z n plus 2, just from the formula. We know that if you had instead plugged in n plus 1, you would get this. Right? So, oh, did I forget to divide? I see. I forgot to divide. Good. I was going to say, why is this still here? You forgot to divide. You get this mess, and then you actually finish the quotient rule. You might get something different, won't you? 2n plus 2. So I'm supposed to get this stuff divided by 1 minus z to the 2n plus 2, right, when you square that denominator. So if you actually finish the quotient rule, you'll get this mess, which... there's the extra n. That cancels and gives us this part. So yeah, we do get the formula that he was saying. I'm saying this cancels one time, okay? And you get that denominator. So we've just shown this. We've just verified that that happens. All right. His next thing was an observation about the coefficients, I guess. We saw already that f of 0 is 0. And the last sentence was like explaining where the, if you plugged in 1, knowing that f1 of z is z, so yeah, you're getting fn plus 1 equals n plus 1 times the previous, right? So that settles, like, what I'm saying is we know this, we already said that, we verified that part, and then like, if you believe this formula, when you plug in 1, you're getting, of course, 0 plus n plus 1 times fn1, like that. So if you just repeat this, if you just iterate this, that implies that fn plus 1 at 1 will be n plus 1 factorial, so that takes care of that part. So that part's easy, the 0 part's easy. The only thing left is like, how do you know that this is a degree n plus 1 polynomial? I haven't thought about it. We know that the first one is degree 1. And so as you go from like 1 to 2, we get z times, we get a z squared there plus a z here. So it seems kind of clear from induction. You see what I mean? If you knew that fn, like if fn had degree n, then fn plus 1 is z times something of degree n minus 1 times z, right? So this is already degree n. Like you're getting z times this chunk of degree n. And then you've got this other number where this is of degree n. See what I'm saying? So you get z times something that's of degree n is of degree n plus 1. So yeah, this recursion thing was the key to the whole. He said something a little more explicit. Maybe that is what I... the coefficients are related by this. Yeah, I didn't bother to write down the coefficients. Are related by this. Yeah, I should take a look at that. This part's kind of obvious, right? Yeah, I didn't see this exactly. I just kind of waved my hands and looked at the overall degree. But he's saying the coefficients that you get look like v, a, v, n. plus n minus v plus 2 av minus 1. Huh. It obviously comes from this, right? Yeah, but I'm not seeing it at a glance. So you just differentiate. So 2a2, so that's this bit, right? Times 1 minus z. Well, sure. So there's that bit when from differentiating. Minus z is, I think, minus v. No, hold on. I think it would be like v plus 1. And then you got this part, n plus 1 times these. So there's, I think that's hidden in there, n plus 1 plus 1 minus v, right? Times the Yeah, I'll have to look at that. I should run for the day. I might make this a little bit more explicit next time. But yeah, this recursion relation pretty much answers the problem. And luckily this is a pretty short section, so I imagine we'll finish this week, even if I spent 2 more days on these next few problems. That'll be the end of this differentiation of power series junk. Series satisfies this differential equation. Okie dokie. The next one. Series satisfies this differential equation. Well, I'm sure it's a lot harder than it sounds. All right, thank you for tuning in today, folks. I'll see if I can make sense of these coefficients at some point, and I'll probably explain it real quick at the beginning next time. But I had better run. Thank you for tuning in, and have yourself a great day.